Greetings, everybody. Learning is a hobby here. In this video, I wanted to finally get around to the solutions to the exercise set for section 3.1 in analysis 1 by Terence Tao. So that's what I'll do in this video. Let me bring up the notes and everything, and we'll just go through the problems one at a time. So let me see if I can share the screen here with you guys. Okay, so before I actually go through the problems here, let me just say that I skipped some parts in some of these because a lot of the proofs are very similar to each other. So, there's no point in just doing the same problem over and over and over again. So I did skip some parts, but I'll tell you that when I get to the problems. Other than that, though, I did all the problems from section 3.1. So after this video, the next couple videos will be on section 3.2 and its exercise set. But anyway, let's not get ahead of ourselves. So here's the questions for section 3.1. The first question says, let A, B, C, D be objects such that the pair set AB equals the pair set CD. Show that at least one of the two statements, A equals C and B equals D, and A equals D and B equals C hold. So here's the proof. Let X be an element of the pair set containing A and B. Then either X is A or X is B, just by the definition of the pair set. Furthermore, since the pair set AB equals the pair set CD, X also has to be an element of CD because AB, since it's equal to CD, has to be a subset of it, right? And since the pair set CD containing C and D has X as an element, X has to either be C or X has to be D, right? Either one has to be the case. So I just take it in two cases. So case one, assume that X is equal to A, then either A is C or A is D. And that implies that for example, if A is C, then B is D, because, the two sets have only two elements in it, right? Then, or if A is D, then B is C respectively, and that takes care of the two cases. Case two, if X is equal to B, then B is C or B is D again, because AB is a pair set. That implies that either A is D or A is C respectively, and that's it. That's all you have to show. I also let me apologize for my voice and everything. I have some pretty bad allergies going on right now, so there's nothing I could do about my voice, and if I end up sneezing on the video, you'll have to excuse me. But anyway, 3.1.2, using only axiom 3.1, axiom 3.2, and axiom 3.3, and axiom 3.4, prove that the sets, the empty set, the set containing the empty set, the set containing the set containing the empty set, and the set containing the empty set, and the set containing the empty set are all are all distinct. For example, that means no two of them are equal to each other, right? And you just use the definitions here, and like I said, the axioms. So for example, the empty set is not an element of the empty set because the empty set has no elements, and that implies that the empty set is not equal to the set containing the empty set. Furthermore, it also means that the empty set is not equal to the set containing the empty set and the set containing the empty set, right? Because the elements are not the same. And maybe I'll just say the other ones are done in a similar way. There's no point in really, I don't know, belaboring the fact here, but you could pause your screen and you could see how I did the other ones, but they're very similar. You just, use the axioms and so on. So none of those sets are equal to each other. All right, question 3.1.3. Prove the remaining claims in lemma 3.1.2. Here, I didn't do that here because I actually, if you saw my summary for section 3.1, I actually already did that in the summary for the section. So there's no point in redoing it here in the exercise set. And same thing for 3.1.4. The question here asks to prove the remaining claims in lemma 3.1.17. But again, I already did this in the summary, my summary for section 2.1. So I'm not going to, recopy it here. You could look at the other video if you want to see that. All right, so going on to section 3.1.5, let A, B be sets. Show that the three statements A is a subset of B, A union B equals B, and A intersect B equals A are logically equivalent. Any one of them implies the other two. Right, so that's what I'm doing here. So I did this in a bunch of parts. So part one, I want to show that a subset of B implies A union B equals B. All right, so here's the proof of that implication. Let A be a subset of B, so assume the hypothesis. Take X in the set, an element of the set A union B. Then, by definition, that means X is an element of A, or X is an element of B. However, A is a subset of B implies that X an element of A implies X is an element of B. Therefore, A union B is a subset of B. Also, B is a subset of A union B is clear from the definition of union, so the two sets are equal to each other. Right? Then in the second implication that I have here, A union B equals B implies A intersect B equals A. Here's my proof. Let A union B equal B. Again, I'm assuming the hypothesis. Take X and A, an element of A, then X is an element of A union B, just from the definition of union. However, X, an element of A union B, implies X, an element of, I'm sorry, hang on. Take X and A. Right. So we assumed that A union B was equal to B. So if we take X and A, and that means X is in the union, but since the union is equal to B, that means that X has to be an element of B. Therefore, A is a subset of A intersect B by definition of intersection. It's clear that A intersect B is a subset of A by the definition of intersection. Therefore, A intersect B equals A. That proves that. That proves that implication. Okay, and then part three, A intersect B equals A implies A subset of B. So let A intersect B equal A. Take X and A, then X is an element of A intersect B. Because if X is an A is in, the intersection A intersect B is equal to A by our hypothesis. Therefore, X has to be an element of A intersect B. Since A intersect B equals A, so that's what I just said. So X is an element of A implies X is an element of A and X is an element of B, which implies X is an element of B. Therefore, A is a subset of B. Right. And now these three implications taken together show that each of the, where is it over here, shows that any one of the the propositions here imply the others. So that's the proof. All right, 3.1.6 says prove proposition 3.1.27. He gives a hint here. He says one can use some of the claims to prove others. Some of the claims have also appeared previously in Lemma 3.1.12. Now, again, I did prove some of these in the summary for section 3.1, and a lot of the other ones, if I haven't proven them, are done in a very similar way. So I only chose to prove some of the ones that are more involved that I didn't do in the summary. Proposition 3.1.27 is about Boolean algebra, by the way. So I only did a few of the parts here. I did part F, I did part G, and I did part H. So I'll go through those, but there are other, there's like A through H, I think, properties that you're supposed to prove for the Boolean algebra question. But like I said, some of them I already proved. The other ones that I didn't prove, besides the ones that I'm showing you here, are all done in a similar way. So, okay, so let's do part F at least. So part F, I want to show that A intersect B union C equals A intersect B union A intersect C. This is one of the distributive laws. There's actually two distributive laws. This is one of them. All right, so let X be an element of A intersect B union C. Then by definition of intersection, that means X is an A and X is an element of B union. Sorry, this my tongue is not cooperating with me. All right, then X is an element of A and X is an element of B union C. X an element of B union C means X is an element of B, or X is an element of C. Therefore, X is an element of A, and X is an element of B, or X is an element of A, and X is an element of C. In other words, X is an element of the intersection of A and B, or X is an element of the intersection of A with C. And that implies that X is an element of A intersect B union A intersect C. And then you could show the other direction as well. So that implies, this subset relation here. And then you could do something. So I won't go through this in detail, but you can do the other thing showing that the right-hand side is also a subset of the left-hand side. And that shows that the two sets are equal. If you want to see that, I won't, again, just because it's very similar and repetitive, you can pause your screen if you want to see how I did that here, but I'll just move on to the next part. Also, I said that was the proof of one of the distributive laws. The other distributive laws prove it in a similar manner, so I just skipped that because it's very similar to each other. All right, let me prove part G next, which is the partition part. We have A union X minus A equals X, and A intersect X minus A equal the empty set. So here's the proof. Clearly, A union X minus A is a subset of X. So consider X in the set X. In other words, I want to show that X is a subset of A union X minus A. That would show that the two sets are equal. Then either X is an element of A or X is not an element of A. If X is an element of A, that implies that X is an element of A union X minus A, right, by the definition of union. If X is not an element of A, then X has to be an element of X minus A. And that implies that X is an element of A union X minus A, again, by the definition of union. So that shows that part. Lastly, assume that A intersect X minus A is not empty. So here I'm doing this by contradiction. Then there's an X in the set A intersect X minus A. So X is an element of A, and X is an element of A minus A. X minus A. The set X minus A is the set, the way we defined it, the set of all Y in X such that X is not in A, which means that X is not an element of A, but that contradicts the fact that we have that X is in A. Therefore, A intersect X minus A has to be the empty set. Right, so that's a proof by contradiction. Right, and the last one is De Morgan's laws. There's two versions of De Morgan's law. I proved one of them, and I skipped the other one just because it's done in a very similar fashion. Right, so here's the one that I did prove: X minus A union B equals X minus A intersect X X minus B. So here's my proof. Let X be an element of X minus A union B. Then by definition, that means X is an element of the set Y in X, such that X is not in A union B. Therefore, X is not an element of A union B, which means X is not in A, and X is not in B, which implies that X is in an element of the set X minus A, and X is an element of X minus B. That implies that X is an element of X minus A intersect X minus B, because it's in both. And that implies that X minus, in parentheses, A union B, is a subset of X minus A intersect X minus B. Okay, and then furthermore, you can show the opposite containment as well. Again, I'll let you pause the screen and look at this. I'm not going to go, it's very similar. So just so I don't, there's more there's more interesting stuff to get to, but you can pause the screen and see how I did it here. And then I also said the other version of De Morgan's law is proved in a similar manner. So in other words, I skipped that, but you can do it in a similar kind of way. So if you want to practice the other, get some practice on this on your own, hopefully you try this already on your own, but you can try the other one and see if you can do it, prove the other version of De Morgan's law as well. Okay, question 3.1.7, let AB, let ABC be sets. Show that A intersect B is a subset of A, and A intersect B is a subset of B. Furthermore, show that C a subset of A, and C a subset of B, if and only if C a subset of A intersect B. In a similar spirit, show that A a subset of A union B, and B a subset of A union B. And furthermore, that A is a subset of C, and B is a subset of C, if and only if A union B is a subset of C. All right, so let's do them one at a time. And actually, I don't remember. Did I do the other? I think I skipped the other ones. Yeah, I did the first three things and I skipped the other three, but because they're done in a very similar way, so you could try those if you want to. But I did the first three propositions here. So let's first show that A intersect B is a subset of A. Let X be an element of A intersect B, then X is an element of A and X is an element of B, just by definition. Therefore, X is an element of A, which implies that A intersect B is a subset of A. All right, just again, by definition of subset. Proposition 2, A intersect B is a subset of B. That's proved in an exactly analogous way to part 1, so I skipped that. And then proving part 3. C a subset of A and C a subset of B, if and only if C a subset of A intersect B. So assume C is a subset of A and C a subset of B. Let X be an element of C, then X an element of A, and X is an element of B. Then X is an element of A intersect B, because it's in both. That implies C is an subset of A intersect B. And then next we assume that C is a subset of A intersect B, and X is an element of C. Then X is an element of A intersect B by the definition of subset, which implies that X is an element of A and X is an element of B, which implies that C is a subset of A and C is a subset of B, just by definition. And then, like I said, the other three propositions are proved similarly, so I just skipped them. All right. And again, I apologize for my clearing my throat all the time, but there's nothing I can do about it. 3.1.8 is they ask us to prove what are called the absorption laws. Let A, B be sets, prove the absorption laws, which are these two here. A intersect A union B equals A, and A union A intersect B is equal to A. So let's prove them. So part 1, A intersect A union B equals A. Let's prove that. And I did this in a slightly different way. I just used the Boolean algebra that we've already established because it makes it a lot easier. So A intersect A union B by the distributive law is the same thing as A intersect A union A intersect B, which is the same thing, right? A intersect A is just A. So that's equal to A union A intersect B, which is equal to A, since A intersect B is a subset of A. Okay, so that proves that one. And say I did a similar technique for part 2. I just used the Boolean algebra. A union in parentheses A intersect B equals A. All right, so here's the proof. A union A in parentheses A intersect B equals by the distributive law, A union A intersect A union B. A union A is of course A. So that set is the same thing as A intersect in parentheses A union B, which is A, since A is a subset of A union B. And that's the proof. All right, 3.1.9. Let A be X be set such that A union B is X and A intersect B is the empty set. Show that A equals X minus B and B is X minus A. So here's my proof. Right, so X equals A union B implies X minus A equals, just from equality, equals A union B minus A, which is equal to B, since if X is an element of A, X is not an element of B. By the hypothesis, A intersect B is empty. And then a similar argument shows that X minus B equals A, but I skipped it because it's very similar to what I just did. All right, 3.1.10. Let A and B be sets. Show that the three sets A minus B, A intersect B, and B minus A are disjoint, and that their union is A union B. All right, so here's my proof. First, we show that A minus B intersect A intersect B is empty. So assume that A minus B intersect A intersect B is not empty. So again, this is proof by contradiction. Then there is some X in the set, some object X in the set A minus B intersect A intersect B, which implies that X is an element of A minus B and X is an element of A intersect B. Then X is an element of A and X is not an element of B, because X is an element of A minus B, which contradicts that X is an element of A intersect B, right? Because if X is an element of A intersect B, it's also an element of B. But from the fact that X is an element of A minus B, it's also not in B. So that's a contradiction, right? Therefore, the set is empty. And then so that shows that A minus B and A intersect B are disjoint just by the definition of disjoint sets. And I skipped the other ones because they're done in a similar way, again, just to skip the tedium of doing it over and over again. The other combinations are proven in a similar manner. All right, so lastly, we show that A union B equals the union of those three sets, those disjoint sets. Clearly, A minus B, A intersect B, B minus A are subsets of A union B. So the union of those three sets is a subset of A union B. So take X, an element of A union B, and then we want to show that A union B is a subset of the disjoint union of those other three sets. All right, so proceeding by cases. Case one, let X be in A, but X not in B. Then that means by definition, X is in the set difference of A with B. Case two, if X is in A and X is in B, then by definition, that means X is in the intersection. X not an element of A, but X an element of B implies X is an element of the set difference of B with A, and that exhausts all possibilities for where X can be an element. Therefore, A union B is a subset of the disjoint union of those three sets, which means that since they're both subsets of each other, they're equal to each other. Okay, 3.1.11, show that the axiom of replacement implies the axiom of specification. So we do that with a direct proof. Assume the axiom of replacement holds. For each X an element of A, let P of X be a property pertaining to X. If A contains no elements for which P of X is true, then the set of all X in the set A, such that P of X is true, is empty, which is certainly a set. The empty set is a set, so therefore the proposition holds in that case. We actually don't even need to use the axiom of replacement there. But then we assume that there is at least one element of A satisfying the proposition P for the other case. And define that. So here's the clever part. We have to define the statement phi X comma Y in the proper way. And the way that you do it is like this. P of X is true and Y equals X, or P of X is false and Y equals A. These are logical operators here. And is the conjunction, or is disjunction, and this end is conjunction. But I wrote it out in English because maybe not all of the people that are watching this have looked at the video on the that I did on the appendix and logic and so on. So, but end and or here are the logical operators, conjunction and disjunction respectively. Okay, so that's a proposition for each X and A. Right, then by the axiom of replacement guarantees that the set of all Y such that phi of xy and X is in A is a set. Furthermore, for X in A, if P of X is true, then Y equals X is an element of that set. And if X is in A, P of X is false, then Y equals A. So that means that X is not an element of the set. Therefore, the set that is guaranteed to exist by the axiom of replacement is precisely the elements of A that satisfy P of X. Therefore, the set of all X in A, such that P of X is true, is a set. And that shows that the axiom of separation holds. And here I forgot to include this when I was writing it up, and I didn't feel like erasing and redoing it. So just here, just as an aside, this set is clearly a subset of A, right? Because that's one of the conditions here. Right. Is this the last? No, I think there's two more. So 3.1.12, suppose A, B, A prime, B prime are sets such that A prime is a subset of A and B prime is a subset of B. All right, there's two parts to this. Part one says show that A prime union B prime is a subset of A union B, and A prime intersect B prime is a subset of A intersect B. And part two says give a counterexample to show that the statement A prime minus B prime is a subset of A minus B is false. And then he asks us if we can find a modification of this statement involving the set difference operation, which is true given the statement, the stated hypotheses. And he says justify your answer. Now he doesn't say you know, I'm assuming you could find like a bunch of different situations, but I just found one that worked. So we'll get to that in a second. All right, here's the proof of part one. So for part A, we want to show that A prime union B prime is a subset of A union B. This is done. We've already done similar proofs to this already like a million times. So hopefully this should be pretty straightforward by this point. Let X be an element of A prime union B prime. Then by definition of union, that means X is an element of A prime or X is an element of B prime. If X is an element of A prime, then X is an element of A, since A prime is a subset of A by hypothesis, and therefore X is an element of A union B. If X is an element of B prime, then X is an element of B, since B prime is a subset of B by hypothesis, and so X is an element of A union B. Therefore, A prime union B prime is a subset of A union B. And part B is done in a similar way. You could again just pause your screen and look at it. I won't spend video time on doing because it's very similar to what we just did. So you can pause your screen and see that if you want to look at it for part B, but it holds as well. Okay, and for part two, here's my counter example, and there's many counter examples that you could pick. I just made one up. So let A equal the set containing the natural numbers between 1 and 6, B a set containing the natural excuse me, the natural numbers between 3 and 8, and then I defined A prime to be the set containing 2, 3, 6, B prime to be the set containing 3, 4, 7. Then notice that A prime is a subset of A and B prime is a subset of B. However, if you take A prime minus B prime, you get the set 2, 6. And if you take A minus B, you get the pair set 1, 2. And notice that A prime minus B prime is not a subset of A minus B. All right, so here's a modification that I made that works. So here, my modification is A prime minus B is a subset of A prime minus B prime. I'm not sure if he was looking for one particular thing that worked, or I don't know. This one works though, and it has the same hypotheses as the original. So, but here's the proof. Let X be an element of A prime minus B, then X is an element of A prime, and X is not an element of B. Since B prime is a subset of B, X is not an element of B, implies X is not an element of B prime, which implies that X is an element of A prime, but not of B prime. That implies that X is an element of A prime minus B prime, which means that A prime minus B is a subset of A prime minus B prime, and that's it. That's the justification. Okay, and this is the last problem, 3.1.13, the last problem in this section, right, where this is the solution set to section 3.1. Euclid famously defined a point to be, quote, that which has no part. This exercise should be reminiscent of that definition. Define a proper subset of a set A to be a subset B of A with B not equal to A. Let A be a non-empty set. Show that A does not have any non-empty proper subsets if and only if A is of the form A equals the singleton set containing X for some object X. All right, so here's my proof. For any Y an element of the singleton set containing X, by definition Y is the element X. Let B be a proper subset of A, then if Y is an element of B, that implies that Y is an element of A by the definition of subset. That implies that Y equals X because X is a singleton set. And that implies that B equals A, which contradicts that B is not A. Therefore, no such Y exists, which means that B has to be empty. Okay, and next I prove the contrapositive of the reverse direction. So here assume that A is not of the form A equals the singleton set containing X for some object X. Then since A is not empty, by hypothesis, there is some object X in A. Furthermore, there must be at least one Y in A such that Y is not X, since otherwise A would be the singleton set containing X, and we said that it wasn't. Therefore, B, if we define B to be the singleton set containing the object Y, that's a subset of A, but it's not equal to A. B is not equal to A because it's missing the element X, and that means that B is not empty. All right, so that proves the if and only if. I did the if direction using contrapositive. So, okay, let me stop the screen share here. Okay, so we're on to section 3.2, which I should have posted at some. I should get the summary for the section 3.2 posted sometime soon. I apologize it took me so long to get the solutions here out this video, but April was kind of a crazy month for me. Plus I went on vacation, so to New Orleans, by the way. But that should be coming out relatively soon, the summary for section 3.2. So we're moving along. And I keep an eye out for my vlog for May, since we're almost into the beginning of May, and I'll give you my breakdown of what I want to get done in May. So keep an eye out for those videos, and I'll see you guys in the next one.